Hello guys, this is 1-1, Properties of Exponents. I'm sorry about not uploading this sooner. There might have been some confusion about participation. I also intended to record this during class, but that ended up not being technologically possible. So I'm going to record this lesson for you guys separately, and we'll see if I can figure that out eventually. I will at some points encourage you to stop this video and try certain problems. Normally I would have you, it would be better, in my opinion, for you guys to wait until the video and to take notes because you'll get some practice in during the notes and it'll work more like you're in class. So hopefully that will work better next time when I have the video up sooner. Again, I am intending to upload on B days instead of A days, so just be watching for these recordings on B days. So just as a quick review, exponents like x to the third power, that just means that we're multiplying x by itself 3 times. And so if you take nothing away from this lesson, nothing else away from this lesson, I want you to know that using this rule, it's not really a rule, I guess, but just using this method, you can normally figure out any problem just by looking at how things cancel when you write them out like this. So I would just encourage you to do that. That's how we're going to sort of discover the rules of exponents today, is to write stuff out and see what happens. So first, we have multiplying terms with exponents. We're going to do an example, x squared. And just as a note, I know these examples are not the same as the ones that are uploaded that you've probably already seen. The other thing that I'm going to do, and sorry for these long explanations, but hopefully we'll get into the groove a little bit better later, but I will upload the notes that I actually take in class onto the internet as well to replace the ones that are already there. Just so that there's some congruency there. Even though they're different, they are teaching the same principles, so if you've already taken notes, that's fine. So anyway, our example is going to be x squared times x to the 4th power. Now if we use this rule that we talked about up here, x squared is just 2 x's multiplied together, and x to the 4th is 4 of them. 2, 3, 4 x's. And so as you can see, since we have the same base, this the same exponent that's being multiplied together a bunch of times, we can actually just count how many x's we have in total, which is 4 plus 2, and that's 6, and rewrite that as an exponent of x to the 6th. I'll just do another example just for good measure. This is going to be y to the 3rd times y to the 4th. And so I'm going to do 3 y's multiplied together for that first term, and then 4, 2, 3, 4 for the second. I apologize if I'm going too fast. Like I said, please pause the video if you're actually taking notes. Otherwise, you're probably fine. So we have 4 y's, 3 more y's, which in total makes, makes y to the 7th power. So the rule here is, as you can see that we've sort of discovered as we wrote out these exponents, the rule here is that you take the exponents, which in this case, let me get my pointer, in this case is a and b, you take those exponents and you add them together. So the rule will say x to the a times x to the b will be x to the a plus b. So you're adding those exponents, and I will just indicate that down here too. Add the exponents. Dividing terms with exponents. If we do a problem like x to the 4th over x squared, writing it out, we see that we end up with 4 x's on the top and 2 on the bottom. And because anything over itself is 1, so for example, like dividing 5 by 5 gives you 1, and dividing y by y gives you 1, anytime you divide something by itself, it gives you 1, which is why we can cancel, that's what we call it, we can cancel the x's that are the same on the top and the bottom. And once we've canceled everything we can, we're left with 2 extra x's on the top, which we can rewrite as x squared. Another example, we can do y to the fourth. I just did y to the fourth. Let's do y to the fifth over y to the second power. So we have 1, 2, 3, 4, 5 y's on the top and 2 on the bottom. Canceling gets rid of 2 of the top y's, and it leaves us with y times y times y, which is y to the third power. So the rule here is that if you have x to the a divided by x to the b, the result will be x to the a minus b. You subtract the ones on the bottom from the ones on the top. So you're taking away from the total because you're able to cancel the ones on the bottom with some on the top. So the rule here is to subtract the exponents. Another example I'm going to give you, because you will see this, if you have like x squared over x to the third power, you end up with 2 x's on the top and 3 on the bottom, which when you cancel, you might notice that your extra x is on the bottom instead of on the top, which you can't just treat the same. Let's see. Because it's on the bottom, it's on the denominator. So that is a divided by x, not just a normal x. So our result will be this 1 over x. Remember that if you have nothing left in the numerator, it's still 1. There's still something there. And just as a note, if we use the rule that we just discovered, we have the exponents of 2 and 3. So the rule says we should subtract those, and this subtraction would be x to the 2 minus 3, which gives you a negative 1. So just keep that in mind for later. Both of these are correct, this 1 over x and this x to the negative 1. Both of those are correct, and they actually are equivalent. So we will talk about why that's true later. Just keep that in mind, that the rule says you get x to the negative 1, and just canceling says you get 1 over x. So just be wary of where your extra x's are. It might be in the bottom and it might be on the top, but just make sure that you know where they are and that they stay there. Raising terms with exponents to a power. So anytime I talk about this later, I'll talk about it using the term power to a power, because there's like layered exponents here, a and b. So you're taking a to the power, or x to the power of a, and then to the power of b. So an example might be x squared to the power of 3. And writing this out, x squared is 2x's multiplied together. And then that third power duplicates that x times x 3 times. So we're taking everything inside of the parentheses and we're making 3 copies of it. So we have x times x, and then x times x, and then x times x. Again, so see that we just made 3 copies of that x times x, which in total makes 6 x's multiplied together. In other words, x to the 6. We can also try y to the 4th power squared. Y to the 4th power is 4 y's. 1, 2, 3, 4 y's. And if we duplicate that, or if we make 2 copies, we end up with y times y times y times y. That's 1 copy. And then one more, y times y times y times y. 1 more copy. And that is a total of y to the 8th power. So the rule here is that when you have a power to a power, or stacked powers, stacked exponents, you multiply the exponents together. So this rule is saying x to the a to the b power. That results in x to the a times b power. So this is our multiply the exponents rule. There we go. So I encourage you right now to stop this video if you haven't already taken notes, and do numbers on the other side of this paper. So we're on page 3 right now. On page 4 there are questions, and so I encourage you to pause the video if you haven't already completed those questions, and do numbers 1, 2, and 3 just to try them. Raising a product to a power. So a product is any 2 things or more than 2 things multiplied together. So we're going to do an example with x and y first, and we're going to do x times y to the third power. So that indicates that we need to make 3 copies of xy. So we have xy times xy times xy. And that's just a bunch of things multiplied together. And it doesn't actually matter what order we multiply those things in, because multiplication is commutative. We can move stuff around and it's still the same. So we can actually rewrite that as just all the x's together and all the y's together, which we can then rewrite in exponential form, which is just x to the third and y to the third. Let's do one with a number. These are truly the hardest ones to remember to do. The key here with products to a power, is that you need those parentheses. If the parentheses aren't there, you don't need to use product to a power. But with parentheses, it's indicating that everything in the parentheses is being raised to a power. So we have 4y to the power of 3. I'm just going to use 3 again. That means we're multiplying 4y by itself 3 times. So to follow our rule, we can just do 4 to the third power, because there's 3 4s multiplied together, and then y to the third power as well. So there's 3 y's. And then 4 to the third power, this is an actual number that we can calculate. So we can actually replace 4 to the third power with 4 to the third power, which is 64. You can check that on a calculator. And then have y to the third power. So this is the answer that MathSpace will take. Even though this is still correct, there's just one more step that we can do. So let's write the rule here. The rule is that everything in the parentheses gets the power. So this will say x to the a. Actually, we don't need parentheses anymore. You can put parentheses, of course, but it's not necessary. X to the a, y to the a. You are just putting that exponent on everything inside the parentheses. It's a little bit like distribution, but it's bad to call it that because that will remind you of multiplying, and that's not really what we're doing. But we are sort of distributing that exponent among everything that's inside the parentheses. So my rule here is going to say everything. Let's spell. Everything gets the exponent. This next rule is pretty much the same. This word, quotient, raising a quotient to a power, that's just a fancy word for a fraction or something that's divided. So my example is going to be x over y, and we're going to do 4 copies of that. So x over y to the 4th power. Again, parentheses are important here. If there are no parentheses, you don't need to use this rule. So you will only use quotient to a power if there's parentheses involved, indicating that everything inside the parentheses needs to be copied. So we have x over y times x over y times x over y times x over y. And when we're multiplying fractions like this, what we do is we just multiply straight across the top and straight across the bottom. Multiplying fractions is the easy one. Adding fractions, you have to do common denominators, but these we just multiply across, which ends up giving us this giant fraction of x times x times x times x over 4 of these y's multiplied together, which maybe you're a step ahead of me. And we have x to the 4th over y to the 4th. So the rule here, and again, it's important that you, if there's a number involved, say if we're doing 2 over x to the 3rd power, when you are putting the exponent on the numerator and the denominator, which is the rule, just make sure that if you end up with something that is an actual number that you can calculate, like 2 to the 3rd, do that, because otherwise it won't take it on MathSpace. So 2 to the 3rd is 8. And you would get 8 over x to the 3rd power. So the rule here is that both the numerator and the denominator get the power. So again, It's a little bit like distribution, but you just have to make sure that everything inside the parentheses gets copied the appropriate number of times. Right here, I would encourage you to turn the page and do numbers 4 and 5. Oops. Numbers 4 and 5. So if you are taking notes with me, pause and do number 4 and 5. So this next one is probably the trickiest rule that we'll encounter today. And that is terms with fractional powers. So the reason that's difficult is because it's really hard to conceptualize what it means to say copy x half of a time. But what I want you to take away from this is that instead of copying x a fractional amount of times, which is like, I mean, what are we supposed to do? Like draw half an x? Like that doesn't help us, right? Mathematically. So what we're actually doing is we are splitting x into two of the identical pieces that multiply back together to get x. So essentially, it's exactly the same thing as square rooting x. We're taking that x and we're pulling it apart into two separate pieces that are identical. And in fact, that's true about every fractional power that's a 1 over something. So for example, 1/3 is a third root. And just a reminder, this little number that we write to indicate that it's a third root, that's only necessary on everything except for, like, we don't have to write this 2 here because it's assumed that a square root is a square root until we put a different number there. So that's just a side note. So even something like x to the 1 over 6 power is the 6th root of x. That's how we say that, the 6th root of x. So we're breaking it into 6 identical pieces because of that 1/6 power. So it gets even trickier here when we get to fractions that aren't just 1 over something. For example, like 2/3, x to the 2/3 power. I can actually rewrite this, and you can double check me on this, but you can rewrite this as x to the 1/3 power squared. And the reason that we can do that is because when we do this, it's a power to a power situation. And when it's a power to a power, we multiply those powers. And that 1/3 times 2 gives us back this 2/3 that we started with. So this is an equivalent statement. X to the 2/3 power is the same thing as x to the 1/3 to the 2nd power. We're just splitting up that power so that we can better understand what it means. Because we know what 1/3 power actually means. It's a third root. And then this 2nd power just remains a power outside of that third root. And that's how you rewrite the fractional exponents into something that we can actually make sense of. So the rule here is that the bottom of the fraction, which in this case it's x to the a over b, so the b, which is the denominator in this case, becomes the root, and the a remains a power. So we're taking the b root of x and then raising it to the power of a. So our rule is that the denominator becomes the root, and the numerator is just a power still. Whoops. So I would encourage you, if you're taking notes right now, to go do numbers 1, 2, and 3 from the second section of the notes on the back. I'll write that second section, 1, 2, and 3. Those will help you practice this like fractional power idea. So now we come to terms with negative powers. Negative powers, like we've already sort of explored this idea up here when we were subtracting because of division. We ended up with an x to the negative first power. which we decided was equivalent to 1 over x. So when we're encountering negative exponents, it's kind of instinct for us to think that that there's somehow going to be like a negative involved, like this x to the negative fourth should somehow have a negative in it. But what mathematicians mean when they write a negative exponent is that we're actually doing the opposite of multiplying. So normal exponents are multiplying something a certain number of times by itself, right? We're actually doing the opposite of that, which is to divide by x 4 times. Instead of multiplying by x 4 times, a negative exponent indicates that we're dividing by x 1, 2, 3, 4 times, which ends up looking like this. So we are dividing by x 1, 2, 3, 4 times, which makes this equivalent to 1 over x to the 4th power. So notice that we went from a numerator to a denominator, and then the power became positive. So the best way to think about this is that whenever you encounter a negative exponent, for example, if we're looking at like x to the negative 2nd power times 5, this should indicate to you, the negative exponent should indicate to you that this is in the wrong part of the fraction. It should be in the denominator. If it's in the numerator and it has a negative exponent, it should be in the denominator, and vice versa, and I'll show you that in a second. But in order to resolve this, we can move that x to the negative 2nd power to the denominator and get x to the positive 2nd power. The 1 doesn't, we don't have to write times 1, you can. But we just moved that x to the negative 2nd to the bottom, and the power became positive. So don't forget that part. The power has to change to be positive. Once you put it in the right place, it no longer needs that, that negative power, indicating that it's in the wrong place, right? We moved it. So an example, perhaps you have an x to the negative 4th power down in the denominator. That indicates to me that it's in the wrong part of the fraction and should be moved to the top and made positive. So that will look like 5x to the positive 4th. It's still over 1, but we don't need necessarily to write that 1 anymore because we don't have anything in the denominator. So our rule is going to say that x to the negative a is equal to 1 over x to the positive a. Careful about that. And I'm going to write here that to move it to the right part of the fraction. So if it's in the denominator with a negative exponent, it should be in the numerator with a positive exponent, and vice versa. If it's in the numerator with a negative, it should be in the denominator with a positive. So right now, I would encourage you to do, you actually have all the tools that you need to finish all the problems, but I'm not expecting you to, in class we didn't finish all of the example problems, but you now have the tools to finish all the way 6, 7, 8, and 9 on the next page. Numbers 6, 7, 8, and 9 of the next page. And that's from the first section. The last rule is the easiest of all of them. You probably have encountered this rule before. But 0 powers, and on anything with a 0 power is equal to 1. 2,846 to the 0 power is 1. So is negative 4,000 to the power of 0 equals 1. If it's x to the power of 0, it equals 1. Any variable to the power of 0 also equals 1. The reason that this is true, and I found that a lot of people don't know this, so it's just kind of an interesting tidbit. Instead of memorizing a rule, you can understand the rule. When mathematicians were trying to define x to the 0 power, since it's not super intuitive as to it's hard to sort of think of multiplying something by itself 0 times. So in order to come up with a definition for x to the 0 power, they looked at things like x squared over x squared. And when we look at this fraction, we know, because of normal math rules, right, if we divide something by itself, since we have the same thing in the numerator and the denominator, that should be equal to 1. Like, no matter what, that's a normal math thing, that if we divide something by itself, it equals 1. And having already made the rules for exponents, right, they also know that if you cancel everything, and if you use that rule of subtraction for fractional, like dividing terms with exponents, you would end up with x to the 2 minus 2, because you're subtracting the things from the denominator out of the things from the numerator, right? So we're taking away 2 from 2, which ends up being x to the 0 power. And so since they knew that these two things had to be equal, this bridge had to be true as well, which meant that x to the 0 power has to equal 1. This has to be true. So that's just an interesting math tidbit there. That's all the rules for you today, and I'm going to end this video in a second, but I just want to let you know that in none of my classes did we do 4, 5, and 6 on the bottom of that page, and in a couple of classes we skipped 6 and 7. So those problems are available to you on the notes, but most of your math homework will be similar to the rest of these problems. Just a reminder that your math homework is on MathSpace. I'm not expecting you to finish these problems, the problems here that you didn't finish. And I never do. In fact, I don't ever make you finish the in-class questions for homework. Your homework is entirely on MathSpace. So just make sure that you fill out the participation for this lesson, and I will see you guys next time.